Hello everyone, and welcome to a video tutorial about electric field. Let me start that with a good marker. Okay, electric field. One of the most important things about electric field is knowing that it is a vector quantity. Now, oftentimes when we're working with electric field, we're going to be dealing with point charges. And the electric field outside of a point charge is equal to 1 over 4 pi epsilon naught Q over R squared. Now, Q is the charge of your point charge. R is the distance out to whatever point you're talking about. Now, we've done a lot of problems with Coulomb's law, which is 1 over 4 pi epsilon naught Q1 Q2 over R squared. And so if you look, you can see that electric field is what's going on outside of one particular charge. Force is what's going on when two charges are interacting with each other. Now, what's often useful for us is to find the electric field and to see how a particle would interact with another charge if it were placed inside that electric field. So, let's say that I have a positive charge. Well, anytime we're looking at electric field and what's happening with electric field, we're going to use what's called a positive test charge, meaning that if I placed a tiny little positive charge right there, I draw an arrow on the direction that it would move, or really what it would feel, what direction of force it would feel. Positive charge would be repelled from another positive charge. So the electric field flows out from a positively charged particle. Then it follows suit that if I have a negative charge, my electric field is going to flow in, like so. Now, when you're doing an electric field calculation, you can find the electric field outside of one charge, you can find the electric field outside of multiple charges. Okay? So, if we were doing an example where we had these two charges and I wanted to know the electric field right here at this particular point, well, I would have an electric field coming like this from this charge, and I would have an electric field coming like that from the negative charge. I would add the two vectorially just like we did with our electric force problems. So you can add electric field vectorially, just like you can add electric force vectorially. Okay. Now, with electric field, let's do a quick example. Let's say I have a negative charge, let's say it's negative 1 coulombs, and I want to know the electric field 1 meter away. Well, electric field equals 1 over 4 pi epsilon naught, which oftentimes we just write as K. Q over R squared. Well, Q is negative 1, but electric field, what we do is we plug in the absolute value and then we assign a direction later. So think about this. I'm using a positive test charge. My electric field would point to the left, which is the negative direction. So I would have an electric field, and it would be negative Q over R squared. Well, Q is 1 and R squared is also 1. So my electric field would just be negative K, or negative 9 times 10 to the 9th. Now, the units on electric field are newtons per coulomb. And that's useful because we get an equation, electric field is force divided by charge. Here's what this equation tells me. If I know the electric field at a particular point, we just found the electric field at this point right here. There's no charge there, it's just some point out in space. If I take a charge, Q, and I put it right there, let's say I take a charge, negative Q. Okay, and let's say it's also negative 1 coulomb. Well, I now know the electric field, and I now know the charge at that point. I could figure out the force. You plug in the electric field, you plug in the charge, and boom, you solve for force. Now, that's all well and good for point charges. But what happens when we have something that's a little bit more complex, like the Van de Graaff generator that I showed you guys, where let's say that it's got negative charge all throughout, okay, all on its outer surface. Anytime you are dealing with a conductor, this is ever so important. Anytime you're dealing with a conducting material, such as like a metal sphere or something like that, all of the charge goes to the outer surface. Because with a conductor, there is no electric field inside the conductor. In other words, as soon as you pass this surface, your electric field is equal to 0. That's because all of the charge is on this outer surface. Okay? And so what we can do is, if they tell you you have a sphere and it's got a radius r, you can still calculate the electric field outside of the sphere. But now, your equation for r squared, r is going to be the distance from the surface of the sphere. It's not going to be the distance from the center, it's going to be the distance from the surface of the sphere. So key take-home point, electric field inside a conductor is 0. And electric field is a vector quantity. So if you have something, let's just stay right here. If you have something like this, you've got a negative charge there, and then you've got another negative charge, and they're the same distance, or they're a distance apart, and you got something right in the middle, and you want to know the electric field at that point. If they're the same charge, then your electric field at that point is also 0. Because think about it. If the electric field, if I put a positive test charge there, it's going to be pulled that way and it's going to be pulled that way equally, meaning it would cancel out. What doesn't cancel out, our next quantity that we're going to talk about, is electric potential or voltage. Now, voltage is a scalar quantity, and it has an equation, VKQ over R. So electric field is KQ over R squared. Electric potential is KQ over R. That looks like a V. Let me make that a little bit more R. There we go. Okay, so what does this mean? Well, electric potential is related to how much potential energy a charge has. Voltage is potential energy divided by charge. So again, imagine that I've got a negative charge, and let's say I put a negative charge out here and I want to drag it closer. Well, the two are going to repel each other, which means I am going to have to apply force over a distance. I put work in. That work that I do is going to be how much potential energy that charge itself gains. Okay? So there's a change in energy involved there. It's the same thing, though, kind of like electric field. It's what's going on outside of one particular charge. The only thing is, it's a scalar quantity, meaning you don't plug in Q as an absolute value. So the example that I did earlier, right in the middle of these two charges, there's no electric field, but there is plenty of electric potential because it's a scalar quantity, meaning you just add the two together. You'd have a potential from this one, and you'd have a potential from that one, and that would equal the potential at that particular point. The only way there could be no potential between there is if I made one of those charges positive. Then I would have a potential from this one that would be negative. The potential from this charge would be positive. The two would cancel out, leaving me with no potential at that particular point. Now, another thing that's kind of groovy, our solid sphere that I drew a second ago, or our metal sphere where I had charge all on the outside. We said that inside the electric field is 0. What's not 0 is the voltage. So the voltage that you'd have, if you think about your R here, your voltage is going to be equal to whatever voltage you had at the surface. And it's going to remain constant throughout. And then as you left, it would get smaller or larger depending on what type of charge you had. So electric field, 0 inside a conductor. Electric potential, constant inside a conductor. So that should get you started on electric field and electric potential type problems.